Hey, I'm Chris from UEI. Before entering in the technical part of this presentation, let me introduce myself with few words. As you can see on the presented timeline, during more than 38 years, my professional activity has been dedicated to aeronautic testing, mainly for a company today named Airbus Helicopter. I was successively in charge of the Avionic benches software development, flight test means, including the hardware and software, the flight and ground segments for the Marinian site. In 2012, I was nominated Airbus Executive Expert. In 2015, I started my active contribution to the ED247 working group. In 2017, I was designated Roadmap Owner for the test domain at Airbus Group level. In April this year, I left Airbus and am now working for UEI, United Electronic Industries, as Director, Avionic System Business and Technology Advisor. UEI is a US company with a solid reputation in the data acquisition and control market, especially for aerospace and defense. During this presentation, we'll go through different aspects of the ED247 standard. The objective and main principles, the benefit, the history, the revision B ongoing improvement, the UEI contribution, and finally the conclusion. ED247 standard is defined by EUROCAE, the European organization leader in the development of worldwide recognized industry standards for aviation. This standard is also called VISTAS, for Virtual Interoperable Simulation for Test of Avionic Systems. Its objective is to define a common standard, allowing to share virtual component models between different aeronautic actors during the whole product life cycle. This includes full simulation, hybrid test benches mixing real and virtual components, simulator delivered to the aircraft end user. One of the main aspects addressed by this standard is the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitalizing and multiplexing them on an Ethernet bus, respecting the timing of the exchanges. This last point is a key one. ED247 standard provides an ultra-light way to virtualize the exchanges between real or virtual components. The capability to log and replay the exchanges between equipment, respecting accurately their timing. An I/O hardware abstraction layer, making the software independent of the hardware. These capacities allow to share and reuse models all along the different development phases, to reuse them for the development of end-user simulator with a minimal amount of effort. Efficient hybrid testing, where we can mix real and virtual components, easily swap between real and virtual component on a bench. To realize distributed testing with the involved component not necessarily collocated in the same building, site, or even continent. Earlier integration testing, even with some components still located at the provider facilities. And wiring reduction and simplification with, as consequence, drastic cost reduction of the bench design and realization. The EUROCAE Workgroup 97, in charge of the ED247 standard, was founded in 2013. The first release of the standard was published November 2017 and include the virtualization of AFDX, ARANG 429, CAN bus, discrete, analog, and non-avionic data. In March 2020, the release A was published, bringing a bunch of clarifications and additional senior virtualization, like serial line, mail bus, voice and video. The release B is planned for Q2 2022. It will include additional capabilities like control and command mechanism, instrumentation, definition of the virtual component delivery format, and additional transport protocols. These additional capabilities will be described in detail in the following slides. Q4 2020, a new cycle of periodic meetings started in order to prepare the Release B. That will include a new bunch of clarifications, additional functionalities, additional implementation solutions bringing better performance, with in mind the backward compatibility with the previous standard versions. In order to work more efficiently, it was decided to put in place 3 subgroups. One around instrumentation, a second one around command and control, and a third one in charge of the miscellaneous topics. The target of the subgroup instrumentation is to define a generic protocol describing the way to monitor the data, those exchanged between the components, real or virtual, and also the component internal ones. Realize failure injection and value overriding of this data. The protocol must be able to define if these actions must be applied at the source or destination level. The target of the command and control subgroup is to specify the following topics: the way to load and start the virtual components, the state machine, the command and control, the health monitoring of the system, and the time management mechanism in different situations that could be encountered, like real-time simulation, execution at the maximum speed allowed by the CPUs when no real equipment is present in the loop, execution at a reduced speed, or even step-by-step during a debug phase. The target of the last subgroup will be to address all the remaining topics, like the validation and update of the MIL standard 5053 aspects, the introduction of new signal types, the potential usage of new transport protocols in addition to the UDP Ethernet defined in the actual release. A first list of candidates has been proposed: DDS, PGM, TSN, share memory. This list will be completed and the advantages and disadvantages of each candidate will be evaluated. This workgroup will also take care of the standardization of the virtual component delivery format, the definition of an ED247 hardware and software conformity assessment process. If you are interested to contribute to the standard evolution, you are more than welcome. Do not hesitate to contact the EuroK Workgroup 97 chairman through its email address, olivier.fourcade@airbus.com. As you can see on this slide, a bunch of UEI products are already compatible with the ED247 published release -A. This compatibility is achieved thanks to a dedicated UEI software. This compatibility concerns all the chassis form factor, cubes, racks, rugged mill, independently of the number of slots, but also a breadth of I/O boards, 12 analog input-output boards, including voltage, synchro resolver, LVDT, RVDT, 8 discrete I/O boards, including TTL and PWM, 7 avionic buses board, including serial line, CAN bus, ARANG 429, and Mailbus 5053. The UEI IO Bridge configuration mechanism is very simple and based on 2 XML files. The first one, based on the ECIC format specified in the ED247 standard, contains all the information relative to the network aspects: IP address and port, structure of the data packets. The second one is based on a pre-existing format, ZML, describe the hardware configuration of the IO bridge, input-output wiring, gain, filter characteristics. These two files are used as argument by the VISTAS application running on the bridge. This application can be automatically launched at the power on during the boot phase. During the past months, different tests have been done in order to evaluate the latency introduced by the VISTAS virtualization. The first one concerned the analog and discrete signals, and the second one the ARINC429 bus. For the analog and discrete, the output of a signal generator is connected to one of the input channels of the acquisition bridge. The VISTAS packets generated by the acquisition bridge are sent through Ethernet to the replay bridge. The signal produced by the generator and the one generated by the replay bridge are simultaneously displayed on an oscilloscope. A step is produced by the signal generator. As both analog signals are displayed on the oscilloscope, it's easy to measure the latency between them with a very high accuracy. For the ARINC429, the way of measuring the latency is a little bit different. The ARINC output of an inertial sensor is connected to an input channel of the acquisition bridge in order to push corresponding VISTAS packet on the network. A PC, the acquisition and the replay bridges are connected to a local network thanks to a switch. The replay bridge generates an ARINC line corresponding to the packets received. This line is connected to a second input channel of the acquisition bridge. Some movements are applied to the inertial sensors. As both ARINC lines are timestamped by the acquisition bridge, the latency could be calculated through the analysis of the ED247 packets. In all cases, the latency measured was below 2 milliseconds. For the analog and discrete, this figure could be improved using higher sampling rate or using on-transition packet strategy for the discrete. Today, the available MIL-STD1553 implementation is limited to the bus monitor capability. Full implementation with bus controller and remote terminal capabilities is under development. One of the most complex scenarios to study is the one described in the slide. It's based on a configuration with the real bus controller and some remote terminals, real or virtual, located on site A, other remote terminals, real or virtual, on site B. The capability of ED247 to ensure the communication between both sites has to be evaluated and the limitation linked to such configuration identified. The fact that the MIL-STD1553 standard requests a remote terminal response time between 4 and 12 microseconds makes this scenario very challenging. In addition to the alternative protocols already presented in the frame of Release B workshops, UEI wants to propose another potential candidate, the LDMA Rocky V2 transport protocol. The main targeted benefits are strong latency reduction. It could be few microseconds on a local network, significant latency jitter reduction, ultra-low power CPU overhead, drastic packet loss reduction, capability to offer light multicast message transfer, efficient usage of the existing network infrastructure, message routing capability over a wide area network. As you can see on this animated slide, the packet transfer between two nodes with the legacy UDP protocol involves multiple copies of the original data buffer, operating system resources usage at different layers, socket, protocol driver, network interface card driver. With the LDMA, the behavior is totally different. The data buffer is directly transferred between the application and the network interface card minimizing the number of copy and system resources usage. The UEI proposed solution is based on the last version of the LDMA over Converged Ethernet protocol, commonly called RoCE v2. Other standards based on LDMA over Ethernet exist, like IRAP, but RoCE is the most widely deployed. It's compatible with 1, 10, 40, and 100 gigabit Ethernet on copper or fiber. The RoCE v2 protocol exists on the top of UDP v4 or v6, so it could be deployed on existing IT infrastructure and routed on a wide area networks. In order to make this technology a lossless one, it must be implemented in conjunction with additional 802.1 standard extensions like 802.1 QBP, allowing level flow control mechanism, 802.1 QAZ, offering bandwidth reservation to a specific traffic class, 802.1 QAU, ensuring end-to-end congestion control mechanism. RoCE v2 is already largely deployed on existing IT architectures in the frame of different application domains like cloud computing, enterprise data center servers, big data, financial services, especially real-time high-frequency trading. As you can see on the slide, key IT players are involved with RoCE. UEI is developing a new CPU board based on the Zinc UltraScale Plus MP-SoC from Xilinx. The main characteristics of this board will be a quad-core ARM Cortex-A53 64-bit processor, a dual-core ARM Cortex-R5F real-time processing unit, an onboard user programmable Xilinx FPGA, 4 GB of 64-bit DDR memory, and 8 GB of flash memory, 3 GB Ethernet ports compatible with IEEE 1588, a full HD 60 Hz display port, an USB 3.1 port, a PCI 3.1 non-volatile memory express drive with a capacity up to 1 TB. This new architecture main benefits will be up to 10 times CPU performance increase over previous UiPath boards, up to 100 real-time performance increase through the FPGA, a Linux kernel with real-time capability. The tremendous capabilities of the UltraScale Plus MP-SoC can be used to execute virtual models, including Simulink models targeting CPU or FPGA fabric, when high performance or low latency interaction with I/O are required. It could be used also to implement many tasks inside the FPGA, like ED247 packetization, LDMA RoCE v2, or TSN. By this way, the system performance could be increased and the CPU power could be used for other purposes, like model execution. The animated schema presented on this slide describes what could be the data path thanks to a RoCE implementation on an ED247 IO bridge. In this configuration, the ARM cores will be involved for configuration, command and control. The real-time transfers will be done without cores or operating system strong involvement. So, the IO bridge will be able to accept a very high number of inputs/outputs, and the latency introduced by ED247 will be reduced to the minimum. It's now time to conclude. The 3 key points you must remember from this presentation are: Point 1. After years of work and meeting involving key aeronautic industry players, The ED247 standard achieves with Rev A a maturity level compatible with an operational implementation. Point 2, the Rev B that will be published Q2 next year will bring additional functionalities like virtual component control on command, access to internal variable of the virtual or real components, error injection and value overriding, standardization of the virtual component delivery format, but also performance improvements, especially in terms of latency, thanks to the introduction of new transport protocols. Point 3, UEI will contribute to the development of the standard and be a key leader for the deployment of hardware in the ED247 IO Bridge market. Thanks for your attention. Do not hesitate to visit the UEI virtual booth where you will find additional video and documents. Ask for a virtual meeting with us during the conference. Later, call or email for more information. I'm now ready to answer to your question if any.